day, the first long day. But we gave you food, so we figured out you should earn it by offering some kind of a big historical perspective on this field that we're focusing, which applies logic to computer science. And we try to see where does it come from historically. Now I'll start with, since we're talking about the iPhone, I'll start with this. This is the Apple logo. And there is a bite in the apple. And people have been speculating, what is the bite in the apple? Okay? And we'll come back to it at the very, very end. Remind me if I forget. What is the bite in the apple? So logic has been very, very successful in computer science. I mean, this day you hear a lot about machine learning, machine learning, machine learning, machine learning, so we tend to forget logic. And that's a whole other conversation. But regardless, we have heard today about many applications. And I'd like to quote Georg Gottlob. He's now professor at Oxford, at Vienna, who said, computer science is a continuation of logic by other means. This is a paraphrase of a very famous quote. Anybody knows? Yeah. Continuation of diplomacy from Clausewitz. War is the continuation of diplomacy by other means. Yes. So, you know, if you're doing logic, you kind of get used to the fact that we use logic in computer science. But actually, it's not clear at all. Why would logic have anything to do with computing? You go and you tell someone, what is logic? They said, well, some branch of philosophy. And you tell them, you know, it's related to the iPhone. And you say, get out of here. What does it have to do with it? And in some article some years ago, Kozma Arshalizi at the Scientific Institute wrote, if a 1901 and talented and sympathetic outsider had been called upon, say by grant-giving agency, to survey the sciences and name the branch that would be the least fruitful in the century ahead, his choice might well have settled upon mathematical logic, an exceedingly recondite field whose practitioner could all fit into a small auditorium. This is a large auditorium here. It had no practical application, not even much mathematics to show for itself. Its crown was an exceedingly obscure definition of cardinal numbers, whatever they are. But before going deeper into the questions of how is logic related to computer science, we have to ask, what is logic? It's not so easy to define logic. Logic comes from Greek. Logos mean, anybody knows Greek? Word. Yes. So what is logic? It's almost an empty word. And for this, we may go to the most famous logician of all times, the Reverend Charles Ludwig Judson, known also as Lewis Carroll. Very good. We have an educated audience here. And here is Alice was a real person. This is Alice Liddell. For her, he wrote the book. And so in Alice Through the Looking Glass, you find the following definition. Contrariwise continue tweedledee. If it was so, it might be. And if it were so, it would be. But as it isn't, it ain't. That's logic. And if that's you're not happy with this 19th century definition, then we can go to a book by a feminist author, Andrea Nye, Words of Power, in which he said logic celebrates the unity of a pathological masculine self-identity that cannot listen and recognize only negation and not difference. So maybe if we want more credible definitions, we'll go back a long time to the most influential intellectual of all times, Aristotle, about almost 2,400 years ago, whose wisdom stood unchallenged for more than 2,000 years. This is a good track record for an intellectual. So really Aristotle is the invented what we call in particular formal logic. And the question that motivated him, how do we distinguish a philosopher? Philosopher literally means lover of wisdom, philosophia. And demagogue literally means leader of the people. How do we distinguish philosophy from demagoguery? And 2,000 years later, Francis Bacon would say it nicely, logic differs in rhetoric in this, that logic handles reason exact and in truth, and rhetoric handles it as it planted in popular opinions and manner. Right? This, as we watch politics today, this sounds very, very topical. Aristotle made an astounding discovery, which is the truth comes out of form. We tend to think that form is superficial and we should look somehow at the inside. But Aristotle said, look at the following patterns of reasoning. All humans are mortal, all Greeks are human, therefore all Greeks are mortal. Yeah, anybody will be convinced, yeah, this sounds like very solid reasoning. Now let's look at the following one. All Bujums are slithy, all Tovs are Bujums, therefore all Tovs are slithy. Now, I don't think you have ever seen a Bujum. If you have seen, you didn't recognize it, and you don't know what are Tovs and why they're slithy, but nevertheless you recognize if all Tovs are slithy and all Tovs are Bujums, all Bujums are slithy, all Tovs are Bujums, therefore all Tovs are slithy. Truth comes out of form. This is terminology, if you don't remember, from Lewis Carroll. So the fact that truth comes out of form is quite astounding, and that's why we talk about formal logic. That's where we talk about formal and formulas. It's all about the form. Now, the Greeks also made another very important discovery. They discovered the paradoxes. Paradoxes are tools for us to sharpen our test our intuition, our understanding. So Epimenides was a Cretan, said all Cretans are liars. In fact, we find it in the New Testament, the epistle of St. Paul to Titus. One of them says, a prophet of their own said, Cretans are always liars, evil beasts, lazy gluttons. They're not just liars, they're much worse than liars. In fact, there is a Hebrew version of it, everyone is a liar. Kol Adam kozev. But actually, if you think carefully, this is not exactly a paradox, because maybe the negation of it is some Cretans are liars. So the sharp version is due to another one, Eubulides. This sentence is false. This is how we recognize today the liar's paradox. This sentence is false. And if you want to have fun, try it with children. And you see, if you are too young and you tell them, they don't get it. They say, can I go play now? But at a certain age, somewhere around 10, or depending on intellectual involvement, they realize that this is really problematic. And you see them deep in thought, what's going on here? And of course, we now understand the key feature of this paradox is self-reference. And we will see the self-reference discovered now, more than 2,000 years ago, will continue to accompany us throughout its story. Now we're going to jump almost 1,500 years. We're going to the Middle Ages when we find Ramon Llull. Ramon Llull was a Catalan monk. In fact, as a young man, he was considered what he later became. He said he was a sinner, but he had an epiphany, became very pious, and he wanted to use logic to convert everyone to Christianity. So here's an argument in favor of the Trinity, of the Holy Trinity. Please follow very, very closely. If in thy three properties there were no differences, the demonstration would give the D to the H of the A with the F and the G as it does with the E. And the K would not give significance to the H of any defect in the F or the G. But since diversity is shown in demonstration, the D makes of the E and the F and the G with the I and the K, therefore the H has certain scientific knowledge of thy holy and glorious Trinity. Capiche? Well, if you don't take it seriously, you're not the only one. Francis Bacon, some person more ostentatious and learned have labored about a kind of a method not worthy to be called a legitimate method, begging rather a method of imposture, which nevertheless would no doubt be very acceptable to meddling wits. Such was the art of Llull. So obviously did not think much of Llull. But Llull did actually, I think, made a contribution. So it's a little bit unfair to make fun of him, because all these letters stand for some assertions. And Llull did understand that one of the things that happens when you start logical reasoning, you have to reason by cases, and you get lots of cases, right? What we call state explosion problem was discovered by Llull. And he built a tool to generate all the combinations. So here you take pieces of paper and you write these combinations on them, and now by start rotating them, you can get different combinations. And he was excited to publish a book. He titled his book, Ars Magna Generalis e Ultima. So this is the title for your book, Great, General, and Ultimate Art. Right? This is talk about self-promotion. Not everybody liked Llull. Late in his life, after he was 80, he went to North Africa to convert the Muslims to Christianity using this kind of arguments, and they just stoned him to death. I don't know why people laugh when I say they stoned him to death. This is a Renaissance painting, the stoning of Ramon Llull. Now, who was influenced by Ramon Lull? This person, the man who brought us calculus and bits, Gottfried Wilhelm Leibniz, a co-inventor of the calculus, huge fight with Newton over priority of the calculus, but invented what we call the binary notation. So if he invented binary notation, he invented bits. So to be the inventor of the bits, I think it's a very important distinction. Leibniz was a prodigy as a child. He taught himself Latin at age 8. He started reading Aristotle. At that time, Aristotle is only published in Latin. He read Aristotle. He wrote a thesis on Aristotelian metaphysics at age 20. Then he wrote another one on logic in the law. And he read Ramon Lull. He wrote later, when I was young, I found pleasure in the Lullian art. And out of this, what we are not too impressed, these rotating circles, which was the first, think about it, it was the first mechanical aid to reasoning. Now, people, of course, had mechanical aid to computation, but this was mechanical aid to reasoning. Out of this, Leibniz developed an amazing dream of a universal mathematical language, which he called lingua characteristica universalis, in which we will be able to write all human knowledge. And furthermore, there will be calculational rule, calculus ratiocinator, a reasoning calculus. And Leibniz knew quite a lot about calculating. He built calculators. And using this calculator, you'll be able to perform logical reasoning. And he wrote, if controversies were to arise, there will be no more need of disputation between two philosophers than between two accountants. I guess he did not know about modern accounting. For it would suffice to take their pencils in their hands and say to each other, calculemos, let us calculate. So he says reasoning, logical reasoning can be reduced to calculation, can be mechanized. This is an astounding idea. Leibniz did not get to carry out his work on this too far, partly because he did not have, unlike his nemesis Newton, he did not have an academic position. He was a librarian to the Duke of Braunschweig, and his main job was to maintain the genealogy of the family, which was very big. He had to spend a lot of time going to archives to track out these genealogies. And so we have to wait almost 150 years for a man of acutest intellect and manifold learning. I just love this title. Please, if you have an influence, write it on my gravestone. And this is George Boole. So George Boole is a very, very interesting person. He was born in 1815. His father was a shoemaker. In 1815, if you were born in England and you are your father is a shoemaker, what are you going to be? A shoemaker. But he was just incredibly bright boy. I mean, at age 12, he translated Horace from Latin to English, and the translation was so good that the principal, the headmaster, accused him of plagiarism. He said, you must have found it on the web somewhere. And his father had to come to his defense. He said, no, it's a real translation. He started tutoring children in mathematics. Then he started tutoring math teachers in mathematics. And eventually, without ever really getting formal education, he became a professor in Queen's College in Cork, Ireland. And in 1847, he published a book. And he had the 19th century is a century of the discovery of abstract algebras. People discovering that you can take the ideas, the algebraic idea that we know from integers and real numbers, addition, multiplication, and you can start treating them abstractly. And you get various algebraic structures, groups, ring, fields. And Boole realizes that logic can be treated algebraically. So in particular, he said, let's take two different adjectives, and we want to take their conjunction. This can be treated as a multiplication operation. Okay? So if X stands for white things and Y for sheep, then X times Y stands for white sheep. So the idea is that logical operation can be thought algebraically was very, very important. And this has come from his book, 1847, The Mathematical Analysis of Logic. And he wrote, the design of the following treatise is to investigate the fundamental laws of the operations of the mind. So this is an amazing thing. He wants to find out the laws of the mind. This is this is, if you think about it, this is the beginning of cognitive science, the laws of the mind. And so here is an example what you get from algebraic treatment. So Boole said, look, if I take white and white, it's just white. That means that I have a new law of idempotency, x equal x times x. White equal white times and white. And now let's do a little bit of algebraic manipulation. X equal x times x minus xx is 0. We factor out x, we get x times 1 minus x is 0. What does this mean? Boole, hey, wait a minute. He says, this says that something cannot be true and false at the same time. You can't be white and not white at the same time. Nothing. And this is called the principle of contradiction. And Boole writes, this is the principle of contradiction Aristotle has described as the most fundamental axiom of all philosophy. Right? This is the basic of truth. Something cannot be, you cannot have two properties, white and not white at the same time. And this is how you go from algebra to philosophy. Now, Boole unfortunately died fairly young. He got pneumonia, and he died fairly young. I visited earlier this year. I visited Cork, Ireland, and they said, "Would you like to visit the Boole's collection in the library?" I said, "I'd love to visit the Boole's collection in the library." So we go to the library, and one of the items is Boole's personal copy of his own book. And they said, "Would you like to hold it?" I said, "Well, this is asking me, Moshe, you know, Moshe is Moses. This asked me if I would like to hold the broken tablets." I said, "Of course I'd like to hold it." So amazingly, because I think it's really, they were irresponsible, they should have asked to put some gloves on me or something, they let me hold Boole's book in my own hands. After that, for a week, I didn't wash my hands. Amazing moment. Now, what we call today actually Boole and algebra are not due to Boole, because Boole thought of this junction as exclusive. And and this gives rise to Boolean rings. If you want the more elegant Boolean algebra, this is due to Gibbons. William Stanley Gibbons, who was a follower of Boole. He was a bit younger than Boole, and he was greatly inspired by Boole. He had a hate-love relationship with Boole, and he continued to think about Boolean logic. And he's written, "I have given much attention, therefore, to lessening both the manual and the mental labor of the process." What is the process? Boolean reasoning. "And I shall describe several devices which may be adopted for saving trouble and risk of mistake." And he goes on to build this device. It's a logic machine. It can reason about 4 Boolean propositions. So the space equal 16 states, but go ahead and see if you can build it using moving wooden pieces only. Okay? This is a special type of transistors. So now it's amazing to see. First of all, he was incredibly excited. You should feel so excited about your own research. As I woke in the morning, the sun was shining brightly into my room. There was a consciousness on my mind that I was the discoverer of the true logic of the future. For a few minutes, I felt such a delight, such as one can seldom hope to feel. Okay, that's how you're supposed to be excited about your dissertation. Now remember, this is a machine with moving wooden pieces that can reason about 4 propositions, and look what Gibbons is writing. The machine represents a mind endowed with power of thoughts, but wholly devoid of knowledge. It cannot be asserted indeed that the machine entirely supersedes the agency of conscious thought. So if we discuss today AI and natural intelligence and what happened, this conversation started by William Stanley Gibbons about machine intelligence versus human intelligence. Now, the final remark is very ironic. I must remark these mechanical devices are not likely to possess much practical utility. Why? We do not require in common life to be constantly solving complex logical questions. Okay? And why is this ironic? Because we jump to the iPhone. If you open the iPhone, you open, and you see there are chips inside, and you go to electrical engineer and you say, "What is this?" And the electrical engineer will say, "Oh, this is the logic of the iPhone." So how did we get from these devices of no practical utility to actually building today? Everybody is here. As you know, I have a hate-love relationship, as you already saw, with these devices. How did it come about? And many people give credit to a very bright young student, Claude Elwood Shannon. Now, all of you, I'm sure, have heard of Claude Elwood Shannon, and he's famous for information theory, and he did information theory was he was quite old, about 29. What did he do when he was really young? So he did a master thesis. And when he was 21, he wrote a master thesis at MIT, a symbolic analysis of relay and switching circuits. What is the key idea there? The key idea here, that when you have switches, they can be open or closed. And that corresponds to true and false. And if you think about what you know a little bit from circuit theory, you should know enough that if you connect switches in sequence, they both have to be closed for the whole thing to be closed, right? So it's an AND. But if you connect them in parallel, it's like an OR. And so this connection between logic and circuits, that's the connection developed by Shannon in his thesis. And Herman Goldstein, who was the project manager of the ENIAC, we're going to meet the ENIAC a little bit later, wrote, this thesis helped to change digital circuit design from art to science, because now we have a mathematical theory how to build circuits. Howard Gardner, a professor at Harvard, wrote possibly the most important, also the most famous master thesis of the century. Okay, you can now Google it and find it. MIT put it on the web, and you can read the thesis. Beautiful master thesis. But actually, it turns out that this connection between logic and computation precede Shannon by quite a lot. And for this, we're going to go back to the 19th century, and we're going to meet a figure of mysterious greatness, probably the greatest American intellect, at least in the 19th century, Charles Saunders Peirce, who was a mathematician, an astronomer, a chemist, a geodesist, surveyor, cartographer, meteorologist, spectroscopist, engineer, inventor, psychologist, philologist, lexicographer, historian of science, mathematical economist, lifelong student of medicine, book reviewer, dramatist, actor, short story writer, phenomenologist, semiotician, logician, rhetorician, and metaphysician. All these were his hobbies. Now, in 1886, Alain Marquand, who was Peirce's student, published in the Proceedings of the American Academy of Arts and Sciences an article called A New Logical Machine, in which he proposed an improvement on Gibbon's logical machine. And the article caught quite a lot of attention. Charles Kendall Adams, who was then the president of Cornell, was quite impressed and wrote to him, "Dear sir, please accept my thanks for your new logical machine. Could you invent a machine that will do the work of a college president? I give you my order in advance." Peirce read the article, liked it, and he wrote to Marquand, and he says, "Okay, but you need to go a little more than what you have done so far. It's time you try to solve difficult mathematical problem. Let's upgrade from wood to electricity, and you can do multiplication and addition." And he drew circuits, how to do multiplication and addition using electrical circuits. As far as we know, Marquand never built that machine, but Peirce was a philosopher. In his mind, it was all done deal now, just the rest was just a small matter of implementation. And he goes on to write again about the consequences of having this logic machine. And he writes, this is 1889. "A logic machine is a machine which, being fed with premises, produces the necessary conclusions from them." Okay, now here is an amazing quote. "The value of a logical machine seems to lie in their showing how far reasoning is a mechanical process. Furthermore, calculating machines are specialized logical machines. If you can do logical reasoning, you can do calculation." And again, remember this all, the philosophy of AI. Peirce is writing precisely how much the business of thinking a machine could possibly made to perform, and what part of it must be left to the living mind, is a question not without conceivable practical importance. So these questions that we think are very modern questions go back to the 19th century. Now, when we talked about mathematical logic, there are two ways we can understand the phrase mathematical logic. One is we apply mathematics to logic, and that was started by Boole. Boole started applying algebra to logic. But the other meaning, that's more modern meaning of mathematical logic, is applying logic to mathematics. And to understand that, we'll go to an article in 1960 by Eugene Wigner, a chemist. He went on later to receive a Nobel Prize. And the article is very famous. It's called On the Unreasonable Effectiveness of Mathematics in the Natural Sciences. And Wigner starts by quoting many of his predecessors. So he talks about Euclid. The laws of nature are but the mathematical thoughts of God. Galileo. The universe cannot be read until we have learned the language and become familiar with the character in which it is written. It is written in mathematical language. Descartes. I allow nor hope for principle in physics other than those hidden in geometry or in abstract mathematics. For in this way, all phenomena of nature will lead to explanation, and induction of them can be given. And so Wigner goes on, and he gives many demonstrations of the unusual effectiveness of mathematics in physics, and he concludes with the empirical law of epistemology. The mathematical formulation of the laws of nature is appropriate and accurate. Mathematics is the correct language for formulating the laws of nature. Now, there are many, many follow-up articles, papers about this, because people say, okay, we accept it, but why is it? Albert Einstein. How can it be that a mathematics, being after all a product of the human thought, which is independent of experience, this is some people debate it, but how is it so admirably appropriate to objects of reality? In fact, Mario Levy wrote a book, Is God a Mathematician? And what is so special about math? Again, Albert Einstein. One reason why mathematics enjoys special esteem above all other sciences is that its propositions are absolutely certain, indisputable, while those of other sciences are to some extent debatable and in constant danger of being overthrown by newly discovered facts. But Pythagorean theorem, we don't think that tomorrow somebody will discover a counterexample to Pythagorean theorem. Why? Because Pythagorean theorem has a proof. The proof has been called the high road to truth. It's an argument that is so tight and so compelling that once you accept it, the debate is over. Debate is over. This is it. It must be true. So mathematics is all about proofs. And for this, we should give credit to the most influential mathematician of all times, not necessarily considered the best mathematician. Maybe this is other people would take this title, but Euclid clearly was most influential, because if you went to high school, you learned plane geometry, and this was some variation of Euclid's elements that he wrote in the 3rd and 4th century BC. And if you look, in fact, for many, many years, if you look at your high school, geometry was a logically perfect science. It was deductive. In fact, you studied geometry because it was such a perfectly deductive science. On the gate of his academy, Plato has inscribed that no ungeometrical person enter here, because the way you learn deductive reasoning was by learning geometry. On the other hand, if you think how you learn algebra and calculus, you are given recipes, and you says, these recipes are true, and why are they true? And the teacher would say, because I told you so. In fact, where is Crystal? Is she here? I was thinking today that, oh, there you are. I was thinking today that in high school, we were taught the sum, how to compute the sum of infinite series, but I don't think we're ever shown that this comes out of linear equations. That just, here is the formula. You should know what is the sum of 1 plus a squared plus a cubed, etc. But we never easy proof in terms of linear equation from which it should follow immediately. Amazing. So this was really the case for many years. Geometry was the queen of mathematics, and algebra and calculus were just servants. But then there is a revolution in the 19th century. And first of all, Euclidean geometry is being dethroned. People discovered there are non-Euclidean geometry. So suddenly plain geometry looks much more arbitrary. On the other hand, a series of mathematicians, starting from Bolzano and ending with Weierstrass, worked very hard to offer us a rigorous formulation of calculus. Instead of saying, d to the x over d to the y, you take very, very small d's and divide by very, very small that. Now, everything is defined by terms of limits. But limits are all in terms of the infinite. So now the very, very foundation of calculus is in terms of the infinite. And that's incredibly problematic, because we are promised these very, very rigorous proofs, and in the very heart of the rigorous proof we find a very problematic concept, the infinite. And the infinite has been problematic for many, many years. We can go back to Aristotle, who said, infinitum actu non datur. He probably didn't say that, that's the Latin version of the Greek. but this is in Latin, infinitum actum natur, there's no actual infinity. Well, you can keep counting, but you can't count to infinite. But already in the 4th century, St. Augustine, a doctor of the church, wrote, what do you mean there's no infinite? You only keep counting finite numbers. But God looks from above, and God sees all the numbers. And there are infinitely many numbers. No one could be insane enough to say that there's no infinity. There is a beautiful book by Amir Akzel called The Mystery of the Aleph. Aleph is a mathematical symbol for the infinite. And he wrote, first discovered by the Greeks between the 5th and the 5th century BC, the Zeno paradoxes are all about the infinite and limits. The concept of infinity was so overwhelming, so bizarre, so contrary to every human intuition that it confounded the ancient philosopher and mathematician who discovered it, causing pain, insanity, and at least one murder we can account of. Okay? In Pythagoras school, one student was murdered over one of these arguments. Amazing. So, if you think that the debates about linear time versus branching time are serious, this is nothing. Okay? No one was murdered so far over branching time versus linear time. And then in 1874, to make things worse, Georg Cantor proves, using, of course, self-reference, there are infinitely many distinct infinities. This is just mind-boggling. It was bad enough to think about one infinite, now there are infinitely many infinities. And so we see how over the years, different mathematicians have very different attitude about the infinite. Leibniz loves it. I'm so in favor of the actual infinite, instead of admitting that nature abhors it, I hold that nature makes frequent use of it everywhere. Gauss hated it. I protested above all the use of an infinite quantity as a completed one, which in mathematics is never allowed, verboten. Kronecker, when he saw the Bolzano-Weierstrass theorem, obvious sophism. It's not a proof, sophism. Hilbert loves it. No one shall be able to expel us from the paradise that Cantor created for us. I mean, to this very day, some people refer to set theory as the Cantorian paradise. And Frege, for the infinite, will eventually refuse to be excluded from arithmetics. Thus, we can foresee that this issue will provide for a momentous and decisive battle. And this was very prophetic. He wrote it in the late 19th century. In the 1920s, such a battle did erupt between Hilbert and Brouwer, and it became very acrimonious, very, very personal fight between them. And now we talked about Frege. Here is a picture of the old Frege, Friedrich Ludwig Goldorf Frege, and one of the most important logicians in history. Why is that? Because in 1879, Frege published a small book, and the book is called Begriffsschrift, a language for concept. And in it, Frege defines what today we call essentially first-order logic. And he says, what is the language of mathematics? He said, in every domain of discourse, there is really the same language of mathematics, with mathematical objects, with relationships between them, with operations on them, with logical operations, Boole, and in the 1870s, people discovered the quantifier. Peirce, one of you discovered the quantifier. Peano in Europe, the quantifiers for all that exist are discovered as transcending just the Boolean operations. So now you can go back all the way to Aristotle. Now when you say all men are mortal, we can write it very formally. It means for all x, if x is a man, then x is mortal. And now we have a syntax using the inverted A for the universal quantifier. For all x, man of x implies mortal of x. Von Heyernoot, who wrote a very influential anthology in 1967, From Frege to Gödel. He was a very colorful logician because he was also Trotsky's personal secretary. And there is a very beautiful biography of von Heyernoot, Logic, Politics, and Love. And he wrote about Frege, perhaps the most important single work ever written in logic, about Begriffsschrift. I think it's an overstatement, maybe the second most important, because surely Organon by Aristotle must be the most important. But this is definitely maybe the second most important. And now enter the picture a British philosopher. Now, for many of these people, the pictures are when they are old, but the contributions are often when you're younger. So this is the picture of Bernard Arthur William Russell. Again, you can see he lived a fairly long life. He lived he almost 100 years. Most of the other people here die either young or miserable or both. Okay, but a few people do get to live long life. Shannon lived long life, and Russell lived fairly long life. Born in 1870. In 1902, when he's 30 years old, he's a young British philosopher. He writes a letter to Frege. And Frege received the letter and started reading it. And the letter is a very nice letter at the beginning. I find myself I write Russell in agreement with you in all essentials. I find in your work discussion, distinction, and definition that one seeks in vain in the work of other logicians. There is just one point where I've countered the difficulty. And this one point became so severe that Frege's book, which is about to comes out the next year, and he writes in the appendix, there is nothing worse that can happen to a scientist than to have the foundations collapse just as the work is finished. I've been placed in this position by letter from Mr. Bertrand Russell. So Russell discovered the inconsistency, we'll see in a minute, inconsistency of Frege's framework, and Frege took it as a shattering blow to his work. This is also happening later on. This is, you think about it, in Germany, in the first part of the 20th century is very tumultuous, lots of traumatic things. And towards the end of his life, Frege became very bitter, became extreme right-winger, opposed to parliament, democracy, liberal, Catholic, the French, and above all, we find in his diary lots of anti-Semitic rantings. So it's a very, very sad end to actually very, very important intellectual career. So what was Russell's paradox about? So the same way that Boole realized that the essence in logic is reasoning algebraically about classes, about properties, Frege realized that it's all about sets. And then Russell realizes that the treatment of sets has a contradiction. And you probably all know it, right? If you take all sets that do not contain themselves as members, is this a set or is not a set? Now this sounds a little bit as a tongue twister. So Russell himself gave a very beautiful parable. He said, consider a small town, and there is a barber who is a man, and this barber says, I shave all men, and only those men that do not shave themselves. And now the question is, okay, does this barber shave himself? In which he should not shave himself, in which case he should shave himself, and you can go on from there. And it's all about, again, self-reference, and Epimenides has spoken from his grave after 2,500 years, and now we found that the very foundation of mathematics has a contradiction. And this became known as the foundational crisis in mathematics. We try to understand mathematics, we went to the sec, we have the infinite and the foundation of all the proofs, we went to sets to understand it, and now we don't even know what is a set. So Russell himself thought he can't just offer a problem, he must offer a solution. And he worked extremely hard on it. He wrote in his autobiography, every morning I would sit down before a blank sheet of paper. Throughout the day, with a brief interval for lunch, remember lunch is always important, I would stare at the blank sheet. Often when evening came, it was still empty. It seemed quite likely that the whole of the rest of my life might be consumed in looking at that blank sheet of paper. So if you're a PhD student and you feel this way, don't despair, because Russell found a partner, which was Alfred North Whitehead, and together they produced not one sheet, but they produced Principia Mathematica. They worked 10 years on it. They produced 3 volumes, 2,000 pages, in which they show how to base mathematics on logic and using type theory avoid the obvious paradoxes. Now this was such an effort that Russell wrote, my own intellect never quite recovered from the strain of writing it. I turned aside from mathematical logic with kind of nausea. So again, what's the moral of the story? Don't take 10 years to do your dissertation. Don't write 2,000 pages. And at first people thought, wonderful, Russell solved Russell's paradox. And then people say, wait a minute. Frege wrote this small book and Russell found a paradox in it. Now we have 2,000 pages. Who knows how many paradoxes are hiding between the sheets, between these 2,000 pages, inside these 2,000 pages of Principia Mathematica. So into this crisis steps in the king of mathematics, David Hilbert, who is, we don't have today such people who are perceived as the topmost mathematician, the king of the hill. We don't have it. Hilbert is one, I'll tell you shortly. But the next one, today mathematics is too large and too diverse to have like one personality that's so greater than life. But Hilbert was one of these characters, and there are just many, many, many stories on him. One of my favorite stories is that one day his students noticed that there is a tear in his pants, and you can see his underpants. Now the question was, who is brave enough to tell her, Professor Dr. Hilbert, that his pants are torn? No one has the courage to do it. So they debate for several days what to do. And then finally someone says, I have an idea. He knew that Hilbert loved to walk and talk mathematics. So he goes to Hilbert and he says, Herr Professor Dr. Hilbert, I hear that the roses are blooming now very beautifully. Can I invite you to take a walk to the rose garden and we will talk mathematics on the way? Hilbert says, wow, roses, blooming, mathematics, what can be better than that? So they go to the rose garden and the students drag him through the thickest part of the garden. And when they finally get out and Hilbert is all flushed with, oh, beautiful roses, beautiful mathematics, the student says, oh my goodness, your pants are torn, it must be from the roses, it's all my fault, I will pay for the repair of your pants, and he starts apologizing. And Hilbert says, no, in fact, yes, I'll tell you a secret. Actually, this has been going on for several days, you're just the first to notice. So Hilbert couldn't take it, there is a problem in the foundation of mathematics. This was for him unacceptable. And in a series of papers and lectures he launches what became known later, when people wrote about it, is a Hilbert's program. And he wanted to formalize mathematics, prove that it is consistent, there are no paradoxes in mathematics. But beyond that, he wanted to prove that mathematics is complete. Every mathematical question can be answered either by a theorem or by an impossibility proof, right? We have impossibility proof in mathematics at this point. And this is really where computer science, you can see computer science trying to get born. Mathematics is decidable. There is a mechanical way to determine whether a given mathematical statement is true or false. This is an incredibly ambitious program. Let's read some of the things that Hilbert wrote. He said he wanted to dispose of the foundational questions once and for all. He wrote, once a mathematical problem must necessarily, he said, every mathematical problem must necessarily be susceptible to an exact statement, either in the form of an actual answer to the question asked or by the proof of the impossibility of its solution. There are no unknowns in mathematics, he says. And here is where computer science comes in. Once a logical formalism is established, one can expect that systematic, so to say, computational treatment of logic formula is possible, which would somehow correspond to the theory of equations in algebra. The way we solve equations mechanically, we should be able to do this, right? This is exactly what Leibniz thought we should be able to do. Calculus ratiocinator. The last paragraph is really not mathematical, it's almost psychological. It says, every mathematician certainly shares the conviction that every mathematical problem is necessarily capable of strict resolution. We hear within us the perpetual call, there is the problem, seek its solution, you can find it by pure reason. So many of you have worked on mathematical problem, and probably, I hope, you have been sometimes stuck on them, and you never said, oh, maybe this does not follow from the axiom of set theory, right? You didn't say that. You thought there should be an answer, I just need to find it. In fact, when I was a PhD student, and I started working on a decision problem in database theory, and then I was a student at Weizmann, and I took a course and I learned about undecidability. I went to my advisor, Katril Berry, and I said, you know, maybe this problem is undecidable. And you say, you've been reading too much theory. This is a database problem. It was undecidable. In 1930, Hilbert retired. He was from Königsberg. The city of Königsberg made him an honorary citizen. They invited him to give a radio address. You can find this radio address. It's been recorded. You can find it. I'm told he has a lovely Königsberg accent that does not exist anymore. And in his radio address ends with very famous 6 words. Wir müssen wissen, wir werden wissen. We must know, we shall know. And these words are today written on his gravestone. Now, the irony is, I want you to look at the date, September 8th, he gives this radio address. Now Hilbert, it turns out that Hilbert's program collapsed completely in the 1930s. Completely, demolished completely. All three legs. Gödel destroyed two of them. Incompleteness was destroyed. There's no systematic way of resolving all mathematical questions. And also Gödel shows that it's impossible to prove the consistency of mathematics. And so this is about incompleteness and impossibility. And then Church and Turing prove that first order logic is undecidable. So there's no computational way to decide the truth of first order formulas. And one of the major characters is Kurt Gödel, that was known as a child as der Herr Warum, which means why? Because as a child, he asked a question, he was told an answer, he would say, but why? And he was given the answer, he said, yes, but why? He kept going recursively deeper and deeper, always asking, yes, but why? Here is a very nice picture of Gödel with Einstein. They became good friends at the Institute for Advanced Studies. And there's all kind of interesting stories about the relationship between Gödel and Einstein. One of them is that Gödel went to become a US citizen, and Einstein accompanied him. And they go to the judge, and the judge says, I hear you are from Germany. He said, no, Austria. And the judge says, oh, well, it's the same thing. And Gödel was very offended. He said, no, it's not. And the judge says, well, nevertheless, this is now, both of them are one country, it's a dictatorship. This can never happen here. And Gödel says, actually it can. There is a loophole in the Constitution. At this point, Einstein started elbowing him and says, not now, Kurt, this is not the right time. And the judge says, let's take it offline. He said, not now, let's not get into technicalities. And it goes on with this, with naturalizing him as a US citizen. The amazing thing is that we don't know what was the loophole that Gödel found. He never told people, nobody asked him, or somehow, if he didn't want to say. After he died, people went through all of his, there was a big project. He never threw away a piece of paper. Every receipt, every bill was there. And 7 volumes have been published of everything that he has written, every letter, every paper. And people found the notebook where he prepared for the citizenship exam. And he said, the loophole must be here. But it was not there. So if there was a loophole, it went with him, or maybe some other politician read it. So remember, when did Hilbert give his radio address? September 8, 1930. On September 7, there is a conference in Königsberg on the epistemology of the exact sciences. And there's a panel discussion in which Gödel said this earth-shaking sentence: one may in fact exhibit sentences which, although intentionally correct, meaning they're true, are not provable in the formal system of mathematics. Right? This is incompleteness. And some mathematicians immediately understood the significance. Von Neumann, who at this point is a young rising star, he's still a young mathematician, and he's been working on the consistency of arithmetics, known as Hilbert's second problem. And as soon as he hears Gödel, he says, oh my God, I've been wasting years on working on this problem. And he says, I will nothing more to do with logic. I will never read another paper in logic. He didn't quite keep his promise, as we shall see. And the big question people ask, this is a day before Hilbert is going to go on radio and says, wir müssen wissen, wir werden wissen. And did he hear it? And we don't think he heard it. We think that he was probably in his hotel writing his radio address. And he missed it. And he never actually quite accepted incompleteness theorem. He thought this was some kind of a mathematical trick, and there should be some way around it. The other person that is responsible to the demise of Hilbert's program is Alan Matheson Turing. What we know today, I mean, that he was of course one of the greatest mathematicians of the 20th century. He was not necessarily the most pleasant fellow to be around, and we think many people think this is speculation. We can know for sure, but based on what we know about his behavior, he may have had Asperger syndrome. Anybody seen Big Bang Theory? Sheldon Cooper? Here is Sheldon Cooper in real life. Brilliant mathematician. So, a group of people, Church, Gödel, also Kleene, Post, Turing, they all essentially gave birth to computer science in about the same time, some cosmic kind of confluence. And remember, the issue was that Hilbert wanted to formalize mathematics. What is the essential element of mathematics? Proofs. What is a rigorous proof? Until Hilbert's time, nobody asked what is a rigorous proof. And people tried to come up what is a rigorous proof. And the answer came, a proof has to be so rigorous that a machine should be able to verify this. Coming up with a proof may be creative, but checking a proof should be completely mechanical. A proof should be machine checkable. But what does it mean to be machine checkable? This is not a formal notion. You must formalize it. So computing is at the very heart of mathematics. You want to understand mathematics? You must define computability. And this came out of the ruins of Hilbert's program. All of our basic concept, the concept of algorithm, that was informal since Euclid. Now it's been formalized. We now know what is an algorithm, even though we still can debate what is the precise definition, because we have more than one definition. The distinction between hardware and software, right? The Turing machine and the instruction written on the tape of the Turing machines. The concept of universality, a machine that can execute all programs. And even the lambda calculus, in some sense, the first programming language, all comes by a group of mathematicians working on the foundation of mathematics. This was not about computation. This was all about the foundation of mathematics. Little did they know that people are already working on computer. In the 1930s, Zuse in Germany is already working on computers. And very soon we will have, we are about to enter World War II, and the ENIAC will come out of World War II. And here you see the ENIAC with Betty Jennings and Frances B. Lash, probably, programming the ENIAC. This is 1946. The ENIAC was not programmed by code, but by setting switches and connecting cables. And if you set one switch wrong, if you connect one cable wrong, the program will not work. So it required tremendous precision and patience. And who has these skills? Only women. Men just couldn't cut it. So all the early programmers were women. You look at picture from the early days, they are all women. Until coding became easy, and then men took over. And now enters the last of the great mathematicians, John von Neumann. So last we saw John von Neumann was in 1930 in Königsberg, where he says, I will have nothing more to do with logic. Since then, then he was still a young mathematician. So in Königsberg, you see he was about 27, 28. Now he's in his 40s, and he's really considered the greatest mathematician, as you may know, game theory, set theory, turbulence, just many, many, many things in optimization, many, many things in mathematics. And there's really there have been no such mathematicians since von Neumann. So the ENIAC was turned on in February 14, 1946. It was an engineering monster. It computed ballistic tables. It was built by engineers. These engineers were fantastic engineers, but there was really no theoretical basis for what they have done. They just built something, and it really worked. How did von Neumann join the project? In August 1944, Hermann Goldstein, who is the project manager for the ENIAC, is standing in a train station in Aberdeen, Maryland, and he sees, to his amazement, John von Neumann is standing there. John von Neumann is the greatest mathematician in the world, and he's a mathematician. He goes to introduce himself, and John von Neumann actually was uncharacteristically friendly mathematician. How do you know the mathematician is talking to you and not to himself? He's looking at your shoes rather than his shoes. But von Neumann actually was a very friendly guy, and he asked Hermann Goldstein, what do you do? What are you working on? And Goldstein tells him about the ENIAC. And von Neumann is incredibly excited. He says, I want in. No one could tell von Neumann no. He gets in. And then two very important reports came out. At this point, the ENIAC is pretty much done, but they're working on the next machine. And in June 45, a famous report, the first draft of a report on the EDVA comes out. And in 46, preliminary discussion on the logical design of electronic computing instruments. And they describe the modern computers. It's based on Boole's and Turing, in fact, also Pitts and McCulloch, the neural net, and all of this. But that gives us what we call today the von Neumann architecture. There's still historical debate about credit, and the people at the ENIAC thought that they deserve some of the credit. There was a huge debate. But here is an amazing quote. 1945, von Neumann says, what we are creating now is a monster whose influence is going to change history, provided there is any history left. How prophetic. Just absolutely amazing. So, these reports get published. People start calling this machine Joniacs, after John von Neumann. They start to build them around the world. In fact, one of the early machines was built in the early 50s in the Weizmann Institute. If you visit the Weizmann Institute, you can see some rotting pieces of the golem, which is the machine was built at the Weizmann Institute. And that means that Leibniz's dreams has come true, right? We started from reasoning. The Greeks discovered patterns of reasoning that gave us logic. Logic gave us computing. And now we close the circle because we have computers that can reason themselves. And going back to logic in computer science, we saw how logic gave rise to computing, but this connection has continuing over the past 50 years, so much so that logic has been called by some people the calculus of computer science. The same way that calculus, if you do engineering, your basic mathematical formula is the calculus. People argue if you do computer science, your basic mathematical reasoning, not to exclude other probabilities emerge, of course, is incredibly important, but logic is the calculus of computer science. And Martin Davis, a very distinguished logician from, if you know about DPLL, the D of DPLL is Martin Davis, and he wrote in 1988 already. When I was a student, even the topologists regarded mathematical logicians as living in outer space. Today, the connection between logic and computers are a matter of engineering practice at every level of computer organization. But I want to go back to something that kind of went through, which is there is a human dimension to the story. And this was put beautifully in a book review by Christopher Dimitro in 2001. And he said, and then there is a human story, the unbelievable and total sadness of it. I told you, almost all characters die young or miserable or both. Leibniz gets into this huge fight with Newton and does not get to advance his dream. Boole died at age 49 because he went to teach class in rain and caught pneumonia. Cantor had depression bouts, and his work was not accepted. Today we think of it as the foundation of set theory, but remember some of the German mathematicians rejected it. They said this is not mathematics, and he died in an asylum. We read about Frege. Hilbert himself lived until 1943. Somehow completely, the world has collapsed. I mean, in the early 1930s, Göttingen is the mecca of mathematics, is the best place in the world to do mathematics. And all of this is destroyed in about 3 to 4 years. There is Saunders MacLean was a postdoc in Göttingen during that period. And he was there and he wrote, what does it like to see the best place in the world of mathematics crumbles in just about 3 years because of Nazism. Gödel said in Austria, eventually he escaped the United States. It was a long trip because he had to cross over Tunon by land, all the way to Vladivostok, and then via Japan come to the United States. And then he died in 1978. He became paranoid. He thought somebody is trying to poison him. He only would eat what his wife cooked. His wife became sick, so he did the logical thing and he stopped eating. We know about Turing and his suicide attempt. And von Neumann himself died from brain cancer. Probably he was involved in the Manhattan Project, and probably that's where he got from the radiation. He ended up dying fairly young from brain cancer. Now, computer science, I think we treat logicians a little better than the way they are treated by history here. And if you go through the list of the Turing Award, the most distinguished award in computer science, you find many awards were given to work on the interface of logic and computing. Rabin and Scott, Hoare, Code, Cook, Milner, Pnueli, and Clark Emerson Sifakis. We heard about the last 2 awards in some of the lectures today. Epimenides is alive and well. He just moved to the humanities. Now postmodernism is not as hot as it was some years ago, where the dogma was there's no universal truth. And of course you just have to ask yourself, okay, is this true? Is this also true or not? And you see again Epimenides. And I want to close by quoting Leibniz, because I think he has, again, his vision. This is an amazing vision. He said, once the characteristic numbers are established for most concepts, mankind will then possess a new instrument that will enhance the capabilities of the mind to a far greater extent than optical instruments strengthen the eyes. And this is, again, incredibly poignant these days, because we are debating whether the goal of computing is to augment our mind or to replace our mind. Thank you very much.